Everybody, it's Mrs. Harbin, video notes 11.2. We're going to talk about LeChatelier's principle, and you have to be able to make observations and talk about shifts in equilibrium, okay? And we'll be disturbing equilibrium, okay? Read section 17.7, put self-check, okay? They're red, they're in the book, they have little check marks next to them. Show your work so that I can check it real quick, but the answers are in the back of the book, alright? So make sure to include the reaction there. Right. So you might be wondering, what is LeChatelier's principle? So here's what it is. This is the long version of it, but it states that when a change is imposed on an equilibrium system, the position of the equilibrium shifts in a direction that tends to reduce the effect of that change. Okay? So we say a change is imposed. That means we're disturbing the equilibrium system, which means we're stressing it out. All right. So how can you stress out an equilibrium or change an equilibrium system? Well, you can add something that's part of the equilibrium, or you can remove it. Now, it might be easy to add. You take a chemical reaction, you add more stuff. But how do you remove something from a chemical reaction? We'll use more chemistry by, causing a side reaction of one of the substances. So I'll show you some examples. Okay, how else can you stress out or change an equilibrium system? Well, you can change its temperature. You could increase it or decrease it. You could change the pressure of the system, and that affects gases. All right, and you can change the volume of the system, but changing the volume of the system really is changing the pressure. Pressure and volume are going to work together to affect gases. So you got to know that. Hey, I'm a dapper looking guy. Okay, so, oh look, it's an equilibrium system with a negative delta H. What if we increase the pressure of this system once it's at equilibrium? Well, pressure involves gases, so this side has 4 gases, this side has 2 gases. All right, so which side will get more stressed if there's more pressure? This side gets more stress, so it shifts shifts away from the stress. So it's going to go from the 4 gas, it's going to shift to the 2 gas, all right? And the reason is more stress on more gas, so then it goes to less gas, shifts towards less gas. Okay, what if we increase the temperature? Well, it all depends where the heat is. Since this is negative, the heat goes on the product side. So if we increase temperature, we're adding heat. In order to increase the temperature, we have to add heat. So if we add heat, we put stress on the side with heat, so it's going to shift away. So it's going to shift left towards reactants, all right, and if it shifts to reactants, the reason it's shifting is more heat, shift away from heat. So it's like adding something from heat. Right. So it depends where the heat is in the reaction. Increase the concentration of hydrogen and nitrogen gas. All right, so that's putting stress on this side because we're putting more stuff on that side. So it's going to shift right towards away from the stress. Okay, more reactant, shift to product, more reactant, shift to product, Okay, increase the concentration of ammonia. So putting more ammonia into the container. More ammonia puts stress on this side of the equilibrium, so it's going to shift left to relieve the stress. More NH3, shift away. Okay. All right. Is there more? So we looked at some examples just now, but what does it mean to add a substance? Well, it means there's too much of that substance. If there's too much of that substance, those molecules will collide more and more and more. And so that rate of that reaction with that added stuff is going to increase until you'll see a shift towards the other side. Okay, so adding too much stuff shifts away from what you added. Okay, removing stuff. It means there's too little of the stuff on that side. So then those molecules can't collide anymore. So the other reaction rate will be faster, and it's going to shift towards what you took away. Okay, I like to think of the removing stuff as leaving a hole in the equilibrium system. What happens when there's a hole? You fill it up. Okay. All right, so pressure. Pressure only affects gases. If you increase the pressure, you're going to reduce that stress by shifting toward the side with less gas. If you decrease the pressure, though, you can reduce stress by shifting toward the side with more gas. Okay, so increased pressure goes away from gas side, from more gas towards less gas. Decreasing pressure goes toward more gas. All right, so make sure you can read and understand these and then apply them. Now, how do we change the pressure of a system? Usually we change the volume. Okay, so if you increase the volume, so you take this container, all right, and then you make it this big. Oh boy, that's a horrible drawing. All right, so I just made the volume bigger, so I increased the volume. So whatever pressure was in this container is now less because there's more room for the gas to spread out. So increased volume means decreased pressure. So if V goes up, P goes down. Okay. How do you decrease the volume? Well, if you take a container, oops, that's like this, and you turn it into that, give it less space. So if the volume of the container goes down, the pressure inside that container is going to go up. Okay, so here's the effects of pressure, and it only affects gases. How do we actually change the pressure? By changing the volume. So you have to know a couple things for that. How do you deal with heat? Well, treat heat as a reactant or product. If it's a positive LTHS is on the left side, it's an endothermic reaction on the left. All right. If you add heat, you're going to shift away from that heat. If you remove heat, it's like leaving a heat hole, and so what happens? Shifts to fill up the hole. Okay, so this is adding heat, this is taking away heat. Hey guys. All right, so hey, it's another equilibrium reaction. That means at equilibrium we have some of everything. All right, if we increase the pressure of this system, we're going to stress out this side with more gas. So we have 9 gas particles, 10. Which side gets stressed? This side gets stressed, so it's going to shift toward reactant. Okay, another way to say that is shift left. All right. Increase the temperature. Well, this is a negative delta H, so that means heat's on the product side. If we add heat if we increase the temperature by adding heat, then it's going to stress out this side and it's going to shift left. Shift left. So we can say shift left or shift toward reactant. If we increase the concentration of ammonia and oxygen, all right, where's ammonia? Here. Or oxygen and oxygen there. That's going to be more collisions here, more stress here, shift away. Okay, shift right. If we increase the concentration of nitrogen monoxide and water, so we increase here, that's stress in this side, it's going to shift away. Shift left. Okay. All right, so a catalyst. Now there's lots of ways to change the reaction rate, and a catalyst is one of them. So here's our energy diagram, or here's our energy diagram. Adding a catalyst, is it going to change the equilibrium? Well, let's see. If we add a catalyst, it's going to make the hill maybe go like that, or it's going to take this hill and make it go like that. So it lowers the hill. All right. But look, this is the forward reaction, this is a reverse reaction. The hill is lower for both reactions. Okay, so equilibrium is achieved faster, but adding a catalyst does not affect that constant that we've been talking about, that equilibrium constant. Okay, so let's do a little more practice. Let's put it all together. Write the equilibrium constant expression. That's the K. So we need the products to the coefficient, all right, a 1, over, oh, look, another product, but solid, so we don't add it, over reactants. Hey, but look, it's a solid, so we don't add it. So the K for this reaction is just concentration of CO2 determines the equilibrium constant. If we add more carbon dioxide to a reaction at equilibrium, we put stress over here, so it's going to shift left. Shift left. Okay. What would happen if we add more calcium oxide? So here's where we get to thinking about what this constant means. All right. This constant depends on the concentration of carbon dioxide. If we add more calcium oxide, this is solid, All right, it's not going to, it doesn't affect the equilibrium constant anyway. It's not part of the equilibrium constant. It doesn't affect keeping this constant, so it's going to have no effect. So sometimes solids and pure liquids don't affect equilibrium because there's nothing dissolved, and so it's just the gases. Right. If we increase the volume, all right, increase the volume means we take the container and we go from little container to big container. Increasing volume means, so this is going to be a high pressure, and this is going to be a lower pressure. All right, so lower pressure means it favors, it's going to favor the side with gas. All right, so this side gets favored. Lower pressure means shift to products. Okay, shift to products. All right, hey, look, it's an equilibrium system. All right, can you see what happened from here to here? All right, so I want you to tell me which side of this reaction has heat on it, and we'll practice it in class. Okay, and then ways we can make changes to that equilibrium. All right, so here's what's going on. LeChatelier, oh, we got to get our disturbance going on. LeChatelier's principle says if you stress a system, an equilibrium system, it's going to shift to relieve that stress. Okay? If we add stuff, it shifts away. If we remove stuff, it shifts towards, because you have to keep that constant. Okay? If pressure goes up, it's going to shift from more gas to less. If pressure goes down, it's going to shift from less gas to more. Huh. It's not a mistake. Look, it's not a mistake, people. It is definitely a ladybug. Okay. Volume. Volume is how we change pressure. Okay. Heat, treat it like a substance. This is the only factor that changes the constant. Okay. So that's why usually at equilibrium at constant temperature, heating something could change the constant. None of these change K. K is always a ratio of products over reactants. Okay. So if we add more products, then their equilibrium has to shift to get back to K. All right. Catalyst speeds up a reaction in both directions, so it doesn't affect the ratio of products or reactants. They just get there faster. Okay. You can determine LeChatelier's principle in terms of K too. So we'll practice that in class. All right. Hey, guess what? You can get some bonus, but do those problems even if you don't want bonus. All right. Because it shows if you understand it. All right, peace out. All right, disturbing an equilibrium system is understanding these 3 bullet points. Okay, make sure you can do it.